Functions can appear in different forms algebraically. Getting them to go Super Saiyan and take their final form can be a bit tricky though. In this section we'll look at Karnaugh Maps as a straightforward procedure for optimizing Boolean functions of up to 4 variables. We can also have maps of 5 and 6 variables, but those get a little bit more difficult to implement. The Karnaugh Maps solution gives us a visual diagram of all possible ways that a function may be expressed in standard form, including the optimum sum of products form. In fact, the expressions produced by the map are always in sum of products form. So, our maps will handle optimization of 2-level implementations, but do not apply directly to possible simpler implementations for the general case with 3 or more levels. Before getting into the nuts and bolts of the maps, let's take a look at cost criteria for constructing a circuit. Literal cost is the number of literal appearances in a Boolean expression. This is simple, but not always accurate. 2 circuits could have the same number of literals, but one could have 2 terms and the other could have 4. That would mean vastly different costs for the 2 circuits. Gate input cost is the number of inputs to gates in the implementation, corresponding exactly to the given equation or equations. This measure is really good since the cost is proportional to the number of transistors and wires that we'll actually use in implementing our circuit. For sum of products and product of sum forms, you can calculate the gate input cost as the sum of all literal appearances plus the number of terms excluding terms that consist of only a single literal plus the number of distinct complemented single literals. This usually works quite well, although the companion website has some pathological examples where this approach does not work as well. The main topic for this subsection is simplification through Karnaugh maps. These are named for Maurice Karnaugh. We'll look at maps of 2, 3, and 4 variables. In making the tables for these maps, we define a min term mi to go with the row of the truth table I in binary as the variable values, so each cell of the map corresponds to a min term. For n variables, we're going to need 2 raised to the n squares. Each map is labeled in 2 ways. 1 with the variables at the upper left of the columns and rows, with a binary combination of these variables for each column and row, and 2 with single variable labels at the edges of the map, applied by a bracket to single or double rows and columns. Each location of the variable aligns with the region of the map for which the variable has a value of 1. This may be a bit confusing, so let's take a look at a concrete example. The preceding discussion may have been a bit confusing, so let's take a look at the 2 variable map structure. On the left, we can see where we can place each min term inside the 2 variable map structure, and on the right, we have the actual min terms in the cells of the 2 variable map structure. In a Karnaugh map, 2 cells are considered adjacent if they differ by 1 literal. The binary combinations across the top and down the left side take the form of gray code. The reason for the use of gray codes on K-maps is that any 2 squares that share a common edge can correspond to a pair of adjacent min terms. We can use this fact to perform simplification by combining 2 active squares that share an edge. A K-map in 3 variables is a rectangle divided into 8 cells. We can think of this map as lying on a cylinder, so the left and right borders share an edge. Hence, we can do things like wrap around from left to right and right to left if necessary. Here's a different view of the 3 variable map. This one is taken from Rosen's text on discrete mathematics that we use here at UH-Hilo. The individual cells here are a bit more clearly labeled by the min terms, and if you want a nice alternative explanation of Karnaugh maps, take a look at chapter 11 in the Rosen text. The K-map in 4 variables is a square divided into 16 cells that correspond to 16 possible min terms. 2 cells are adjacent if they differ in only 1 literal. You can think of this one as lying on a torus. A torus is a surface of revolution from a circle going around an axis that is coplanar with the circle. Of course, it gets more complicated when you look at these from a topological standpoint, and there are actually several different types of tori that you explore in topology. Again, we can wrap left to right and top to bottom. Can we have more than 4 variables? The answer is yes. It does get tricky from a geometry standpoint, but we can still make maps with 5 and 6 variables. For more than 4 variables, we use rectangles of 2 raised to the floor of n divided by 2 rows and 2 raised to the ceiling of n divided by 2 columns. We position these so the cells differing in just 1 literal are adjacent. And again, we use gray codes to arrange the rows and columns of the map. We can use the same process to minimize. There are 4 steps to using a K-map to minimize a function. It's a little bit more confusing than doing the time warp from the Rocky Horror Picture Show, but should still be achievable. So let's give it a go. Step 1. Enter the function on the K-map. You can do this by using the truth table and putting 1s on the map for the active minterms. Step 2. Identify collections of squares or rectangles on the map, representing products terms to be considered for the simplified expression. Want to find the fewest such rectangles. Step 3. Determine if any rectangles are not needed. Rectangle is not required if it can be deleted and all the ones remain. And if you've got a choice, try to keep the largest rectangle. After you have your required rectangles, you simply read off the sum of products expression. And you're done. Let's take a look at an example. You can find several different examples on pages 67 to 70 of the text. Here's one with 3 variables. Consider the equation x, y, z naught plus x, y naught, z naught plus x naught, y, z plus x naught, y naught, z naught. The minterms that are present here are m0, m3, m4, and m6. As a first step, we can draw out a template for a K-map with the minterms indicated in the square brackets. Next, we place the minterms m0, m3, m4, and m6 and set those to 1 on the map. We set the rest of the minterms equal to 0. Next, we identify the rectangles on the map. Now we get the equation. The one for the left column is y naught, z naught. The wraparound in the bottom column is x, z naught, and then all by its lonesome is x naught, y, z. So the whole equation becomes x naught, y, z plus x, z naught plus y naught, z. This can often be a bit confusing at first, but we'll have some examples to work through for the homework so you can become a pro with Karnaugh Maps. Don't forget to check the La Lima site for assignments, and if you want extra examples, the Mano textbook is good, and the Rosen textbook has a lot of examples in Chapter 11.